Hello and welcome to today's seminar, From Manufacturing to Recycling, Benefits and Use Cases of XRF along the battery value chain. My name is Frank Portala and I'd like to guide you through today's seminar. First of all, I'd like to give you a brief outline about our seminar. So after an introduction, we will show you the applications during the upstream process in more detail. After that, we will switch to the lab and show you the analysis of cathode and anode materials. Back in the studio, we will show you applications about battery recycling, and then we switch back to the lab for a second session about the black mass analysis. After that, we will conclude our seminar with a summary and then switch over to a Q&A session with our experts. Today's speakers are Kai Behrens and Adrian Fiege from the XRF product management team in Karlsruhe. And for the lab sessions, we will switch over to Hannes Lüers, who is our application specialist XRF in Karlsruhe. And with this, I already like to hand over to Kai and Adrian. Thank you very much.
Many thanks, Frank, for the nice introduction and also welcome from our side. My name is Kai Behrens and with me is
Adrian Fiege.
Yeah, and we welcome you to our today session about the battery value chain. And we have a short introduction here.
Yeah, Adrian, so I get started. So also very warm welcome from my side. So let's dive into today's session. So what is very important to acknowledge for batteries and battery manufacturing is that we have really a significant increase in demand already, and this will even go further. So here we see just a projection for the next coming years until 2030. So we expect really a growth of the output of the demand by about 30% per year. And this is, of course, because of the energy transition we have, the changes in the political environment also. And with such a gigantic ramp up, there's, of course, also the momentum for the industry to seek more efficient, more cost-efficient production ways to also keep the quality of the products of the battery at a very high level and to ensure that the performance may also increase of the batteries at the same time.
Yeah, the very exciting thing is we are witnessing a disruptive technology change, like the introduction of the internet. This really changes the industry. And of course, it's pretty attractive because a lot of nations will become independent from combustion and from energy resources they don't have. So they can generate the power by themselves. And yeah, let's have a closer dive into this topic.
Yeah, so to really facilitate this transition, you need analytical tools, and this is our topic today. So today we are talking about XRF, and here's a little bit of a snapshot of the battery value chain. And so XRF is really used at the very beginning, so for mining. We'll spend a few words about that. Then it's used for the raw materials. And before we get into the cells, we also look into the upstream production process and its applications with XRF a bit more into detail. And then later on, XRF plays a really important role in recycling. So we also have the opportunity and also the requirement to regain the valuable resources from the batteries and enter them again into the production process.
Yeah. What is interesting is that XRF is the established technology in the very beginning, the mining and the raw materials, but also in a few other steps in similar industries. And what is really exciting here to learn that the recycling is already in focus when this technology is growing. And the reason is quite simple. It's not rubbish, it's a resource, a valuable resource. We want to recover early in the process.
Yes. So for those who are not familiar with XRF, we have just a very brief overview of what XRF is. So with XRF, we basically have an X-ray beam, which comes from an X-ray tube that hits the sample. and it excites then the inner shell electrons within the sample. So in this process, you have as a next step an outer shell electron that falls into the vacancy, and with that we are emitting X-ray photons. And these X-ray photons have a characteristic wavelength and energy, and we can detect that and therefore then determine the composition of the sample. If you want to learn a little bit more about this, you can watch our video, What is XRF, on YouTube. This is quite nice and educative.
The most important thing, or the learning we can have here, is that we are looking at an inner electron shell electron, and actually so it's independent from the chemical binding. And this is important because therefore it gives a lot of freedom to XRF, which we will learn later.
Exactly. So one of the systems that we provide is the S6 Jaguar, which is our wavelength dispersive X-ray fluorescence spectrometer. Maybe Kai, you can spend a few words on the S6 Jaguar here.
Yeah, actually every XRF system looks a little bit similar. Means we have here an X-ray tube which excites the sample, and then actually we have an outcoming fluorescence beam which enters the goniometer. There is a technology with a semiconductor detector. It's called energy dispersive. This is on the detector side a little bit easier. Nevertheless, the S6 Jaguar is very compact. It's a benchtop instrument, but has the advanced technology of wavelength dispersive XRF. So what happens here is that we have analyzer crystals which are separating the incoming beam into the different energies. And then we have two detectors which travel to the position where this energy needs to be recorded. And with the flexibility in the excitation voltage from 20 to 50 kV and 1 to 17 milliamps, actually we can fine-tune the excitation and the detection of each element, which then leads to a very nice analytical power. So this sounds a little bit complicated, but the instrument does the setting by themselves. So it knows which crystal to use, to which position to travel. So this is all automized. The only thing we need to do is to tell, hey, those are the elements I'm interested in.
Yeah, Kai, you mentioned that there are different types of devices, different classes like energy, wavelength dispersive, benchtop, floor standing. It always depends on the application which to choose, and there we can provide the necessary guidance. So overall, X-ray fluorescence can really cover a broad range of elements, not starting from lithium, that's not what we cannot detect, but other than that, we can detect most of the periodic table. And as you will see throughout the talk, we can even go to very low concentrations, even for elements such as sodium in terms of the detection limit. And we can cover traces as well as major elements up to 100% in one analysis. So this is a very important feature of XRF.
Yeah. There are some gray elements we cannot analyze directly, but there are ways even to see and to evaluate those non-measurable elements. For example, the rest to 100, the Compton ratio. This is the scattered radiation coming from the X-ray tube, which tells us about the sample composition, the general sample composition. So we can access also non-measurable elements or by stoichiometric ratio. So therefore also it helps to work for lithium or oxygen, right?
So maybe Kai, you can tell us a bit more about what type of samples we can analyze in XRF, and maybe also a few words on sample preparation.
Now I want to solve the riddle from the beginning. The big advantage of XRF, I said we are analyzing, or we are using an effect in the atom shell which uses inner shell electrons. And this, therefore, we are independent with XRF of the chemical binding and also the state. So we can analyze loose powders or liquids. So these can be filled into liquid cups, which are shown here, and analyzed directly. So there are some pros and cons. The one thing is the grain size can have an influence. Also, homogeneity might be a factor, but nevertheless, that's a very quick, easy way. You fill the powder or liquid in, analyze in the instrument. If we want to have a little bit higher in the intensity, sensitivity, if we want to be more representative with the sample, we press the powder with a little bit of winder after grinding into a stable pellet. Those can be stored also for years. Nevertheless, solid samples we can cut into shape and analyze directly. Sometimes we need a little bit of polishing. Think about a coated metal sample or a painted metal sample. We need to see the bare metal. That's it. Foils, quite interesting, can be analyzed directly. Means take one of the liquid cups, use this liquid cup to stretch the foil and then analyze it directly. And last but not least, this is not a topic for today, but for some reference samples, for very high accuracy, very good precision, we can melt the sample with some borate salt and transform the sample into a stable glass bead. So then we have very homogeneous result. The thing is, we are not working with just 100 milligrams. This can be done as well, but typically we are working with a sample amount of 5 to 10 grams, which also helps to increase representativity of our specimen analyzed to the big batch we see in the production.
Yeah, so just a little bit of a spoiler here. You will see that throughout the talk. In battery applications, what you're mostly looking into is loose powder, liquid analysis, and sometimes pressed pellet analysis. So this is all something that can be done easily after minimal training and within the matter of really 1-2 minutes. Yeah. However, there's also other elemental technologies, and one of the key ones here is inductively coupled plasma spectrometry. Can you maybe mention a few words why this may be competing or not with XRF?
Yeah, so whenever we look into service labs, we see handling hundreds of different samples. Actually, we see a lot established ICP. It's inductive coupled plasma, and then we have optical emission or a mass spectrometer. They are covering wide element ranges and concentration ranges. They're with some dilution. The benefit is it's one recipe to fit all. The problem is that you need a lot of hazardous chemicals. You need to transform the solid sample or the powder sample into a liquid form, which need acid digestion. And here the trouble starts. You need trained lab technicians. You need suitable laboratory, including a fume hood. And actually, you need to handle hazardous chemicals with all hazards in occupational health and safety regulations. So actually, and you need to work with the instrument. Daily instrument calibrations will call for a lot of work time you spend on maintaining the instrument and the calibration. So therefore, it's a good technology when you have a lot of different samples, but when you need to have a quick answer, this doesn't work.
Yeah. So basically, the point here is that the ICP OES can really help you maybe in a central lab, also maybe in R&D environment. That's really a good tool here. But when we are thinking back to how much we want to upscale and how much we then need to upscale and our throughput also in production monitoring, this is where XRF really comes into play.
Yeah, we have here a comparison actually. When you look into solids, means we have learned that with XRF, we take the sample, we grind, we press it, and then we analyze it. A compact sample we can analyze directly. When we think about AAS or ICP mass spec, we see this long blue bar up here, and actually this is the acid digestion time. And then when we think about the cobalt or manganese solution, we have a high concentration. We need a dilution step. So therefore, we are spending a lot of time waiting that the sample is finished. This takes easily a couple of hours in a normal workflow. So the time to result is pretty quick with XRF, within 5 minutes, and we talk about hours with ICP mass spec. For liquids, the advantage is not so there, but nevertheless, it's also, you need to start the instrument, you need to calibrate, and you need to dilute the sample, and with XRF, you simply put it in, and that's it.
Yeah, the calibration is valid for a very long time, and you can simply even facilitate 24/7 monitoring here.
Yeah. So the thing is in total much higher sample throughput, a long-term calibration. So you invest effort once and then you are done. And then actually we ensure shortest time to result, which helps in production.
Exactly. So now let's dive into some real examples, really more from the upstream production process, Kai. And here I want to start with a bit of an overview first. So we see here depict the lithium NMC cell inside. And what is already quite interesting that most of the materials inside that cell can be analyzed and are already analyzed by XRF, maybe just in some very different industries, like for instance polymer production, which is supported by XRF and others. In upstream processes for the battery manufacturing, however, we are looking into some of these materials more significantly, while others may play a lower role in terms of analytical need for XRF. So some of the most important ones are checking your raw materials. So this can be checking your nickel sulfate in terms of purity, but also making sure that it is actually nickel sulfate, or your cobalt sulfate, iron phosphate. You can all check, we can all be easily checked in a liquid cup with the push of a button. Then we will look into cathode materials, anode materials like graphite, copper foil, aluminum foil. This can also be done by XRF to verify, get an idea about the potential contamination. And later on in the process, when we really produce the cathode active material, we are looking into stoichiometries and once again purity, so something that might come from the raw material or might come from the production process. That could be residual sulfur, for instance, in your cathode active material.
Yeah. So actually the most important thing, the learning here is XRF is established for all those materials, but maybe in a different industry. This is the one thing. The second thing, it's not just helping with the major element, but also to recognize impurities, contaminations which might occur when handling large batches of samples like a ton of salt or whatever. Mm-hmm. So actually this is where XRF plays a vital role already in the industry today.
Yeah, exactly. So when we talk about battery manufacturing, we of course immediately think not only about mobile devices or so, but nowadays a lot about electric vehicles. And especially when you think about electric vehicles, it's of course not just the inside in a cell where XRF or analytical tools in generally play an important role, but it's also everything around. So it can be the casing, it can be the racks for the batteries. So here we look into, we need a lot of aluminum, for example, we need a lot of cobalt, we need a lot of manganese, nickel, lithium. Here's just an image from a Tesla factory, for example, indicating a little bit by volume of how much of these materials you need for a gigafactory. And Bruker provides a lot of solutions for these different materials. This is not only XRF, but also OES and CGA, for example, and X-ray diffraction.
Mm-hmm. Means then this is actually where you need to understand the entire material flow, and this is where analytical tools from Bruker will help you throughout the entire production chain.
Yeah, and where everything starts is actually at the mines. Mm-hmm. For a lot of these metals. And maybe Kai, you can explain us a bit why XRF is so important for mining.
Yeah, means we learned that the technology is quite robust on the one hand, but also handles solid samples directly with a high precision and accuracy. And when we look into mining operation, that's a big investment, and actually it's a valuable material flow. So on the one hand, we need to determine very accurately the ore grades or the grades of the concentrate. So the value determined element, is it copper, nickel or cobalt? But also there are some impurities involved in the value chain, means when we look at penalty elements. So when we understand copper ore can contain arsenic and lead, which will lead to later on to negative effects in the product. In iron ore, when we think about copper, silicon or phosphorus, this actually will determine also the value of the iron ore. Or toxic elements in coal which will have a negative influence, or the sodium and lithium salts. The sodium can be analyzed by XRF directly, and so therefore we can predict, okay, what will happen when we use this salt in a battery, avoiding the overheating. So actually XRF is the analytical tool in the mining process, and so therefore better keep it, right?
Yeah, exactly. So that's here the take-home message for the battery session today is basically XRF is the established method for these materials. And this means, well, it's probably the ideal method to also check these materials when you receive them. Maybe a few words about anode graphite. So that's one of the materials that you might receive. And this is something that you can measure, right, Kai, quite well on the Tiger, no?
Yeah, I mean, actually we learned, we work with 400 watt excitation power with a benchtop instrument. Nevertheless, we also have a floor standing model which works with up to 4 kilowatt. And the reason is quite simple. For graphite, we look at low 1 ppm detection limits. So we want to really understand the impurities. So especially elements like sulfur, chlorine, but also elements like copper. So they can have a negative influence on the anode. And so therefore, we need a powerful detection method. You see here, it's very easy. We press the graphite powder with a little bit of wax into a pressed pellet, and then actually analyze and see directly cobalt starting from 0.3 ppm, which is excellent. So the purity can be easily accessed, and you can control the incoming material if this is according to spec or not, right?
And there, I mean, some of these elements can really be quite dangerous when it comes to, battery lifetime, battery safety also, like sodium, which can cause overheating of the battery. So there you really want to see that you get to the really low concentrations to ensure that your battery performance is also right. And this gives you also the strength to really evaluate suppliers that provide your graphite. Yeah. So as a next step in the let's say upstream production process, we want to have a closer look into the cell. So one point here we need to acknowledge is that currently when you have an electric vehicle, the battery makes up a huge portion of the costs, maybe up to 50% even. So this is something the industry, of course, is challenged with. In order to reduce production costs for electric vehicles, they need to work on the batteries. So the batteries need to be manufactured cheaper while still having the same quality and even improved performance. So there's a lot of challenges involved. So this really means that we have to look closely at what technology we use to monitor our processes. And maybe having a little closer look and very in a timely manner can really help us to facilitate producing high quality batteries. Yeah. And one more point here is that if you look here in the graph on Kai's side is also the value. So the value in a cell is mostly made up by the metal values in the cell. And the big part here comes from the cathode material.
Yeah. So actually this shows also the challenges for traditional car manufacturing. Suddenly to have a burden of something like 16% in material cost for things which they don't have on usual traditional combustion engine models. And actually this is where XRF can help you to improve, let's say, to be in spec, but also be cost efficient. And let's have a closer look how this works.
Exactly. So with lithium batteries, there are several types of cathode active material which is being used. And here just 3 main types being listed. So the most important one is the lithium, nickel, manganese, cobalt oxide, abbreviated as NMC or lithium NMC, which has a very high density and is simply very suitable for electric vehicles. But there are also other technologies. One of the more affordable but a little less performance is the lithium iron phosphate, LFP. And then we've also a LMO here, which can play an important role for lithium type of batteries. On Kai's side, you see a bit depict one part of the upstream processes where our technologies, Bruker's technologies, plays a very important role. We already spent a couple words on raw materials, and this is, of course, where XRF plays an important role. Then what we do with these nickel sulfates, nickel cobalt sulfates, and so on, typically they go in a solution, and then they are mixed. And these mixtures, so not only the raw materials, but also these mixtures can be verified in terms of their stoichiometry, their purity with XRF. Later through the process, at some point you have the dried hydroxide precursors. This is here in the middle of the diagram. This is where you use XRF, but also XRD to check the quality. And then before you start really producing your cell, you might want to check again. You might want to check again whether the ratios are fine. So nickel, manganese, cobalt is in good shape. But also you want to check, for example, is there any residual sulfur or maybe even sodium present? And therefore, for those elements, you can then determine thresholds and also for the ratios to make sure your production processes are in good shape.
Yeah. Again, as a reminder, all those two technologies are working with solid samples and pretty quick. So simple sample preparation. So therefore, they can be done pretty short prior to the production step. And therefore, there is not a long delay time where material need to wait for the release, right?
Yeah.
And yeah, I guess it's now time to look at some of the applications, right?
Exactly. Before we dive into the applications, though, just a few more words here. So, for example, there are different lithium NMC types. Currently, there is a development of, for instance, reducing the amount of cobalt in that. So we are starting with something where we have a molar ratio of 1 to 1 to 1. That's also called NMC 333. Has been used in a BMW electric vehicle. And now we are progressing more to a higher nickel content. And that has different reasons. It has performance reasons, but it has also reasons for the availability of cobalt. So cobalt is simply an element that is not so abundant in terms of availability on the market. And then, of course, with these different types there and with changing types, the requirements also can change. And XRF is a very adaptable technology, so it can grow with these tasks.
Yeah.
So you can measure all these types, obviously, with XRF.
Yeah. Yeah. So actually, maybe the user is not only interested in the concentration, but more about the stoichiometry, right? And this is quite an interesting application XRF can easily address.
Exactly. So what we've done here is basically looking into liquid precursors. So you take from a nickel manganese sulfate, a cobalt sulfate, you get it into solution, you mix it according to stoichiometry, and then you can essentially check it. So here you can easily produce a calibration based on nickel sulfate solutions on a system like our energy dispersive system, the S2 Puma. And then you can run your quality control checks by simply pipetting something like 5 milliliters into a liquid cup, and the measurement is done in 2 minutes. So preparation takes 1-2 minutes, measurement 2 minutes, 3 to 4 minutes, you're essentially done with your results.
Yeah. Actually, when we see here the calibration curve means they are straight, so it shows it's a straightforward process, and we see the correlation coefficient, it's close to 1. I guess it's a no-brainer. XRF can be calibrated and can be very accurate.
Can be calibrated, can be very accurate. Yeah, these are the calibration curves here for the 3 elements. In this case, we just focus on the majors. Of course, we can also calibrate the traces and contaminants in the system and achieve a very good calibration curve and precision. And one brief look into our software here. There's a snapshot from our software, left-hand side. You see how the results can appear. You can, like Kai said, you can express that as concentrations, elemental concentrations, oxide concentrations, whatever you find more fitting. You can also transfer this into maybe a more useful space for you. So you can transfer this into the molar ratios according to the NMC type. So you can, for example, say, oh, you have a 6 to 2 type, how close you are to the 6, to the 2, to the 2. And based on that, you can determine thresholds. So for the operator, it's very easy to make a decision based on the threshold. So if something red pops up, it means simply out of spec, we have to do something, whatever our standard operation procedure defines.
The big advantage here also we wanted to point out, you see there is the spectrum shown, and actually whenever a sample is out of spec or you get a warranty claim that sample cells of a production batch might not perform as well, you are able to look at the spectrum and actually see if there is a contamination maybe. So maybe the ratio is okay, but there might be a contamination which leads later on to performance issues. So actually you can evaluate all those spectrum. They are stored in the instrument even after weeks. You can go back and see, oh, then this batch had a problem, and you can see and evaluate if this was the precursor material you have used.
So, and yeah, last but not least, for this liquid precursor use case, just a precision test here. So what we've done, we basically remeasured the sample 12 times. We prepared it each time, we loaded it each time, so really like as in the real world, not measuring the same sample every time. And you can really see that we have an extraordinary stability here. We produce a relative standard deviation of around 0.1% for nickel, manganese, and cobalt. And we can then, of course, determine relatively easy what are our thresholds and meet them, and that in just 2 minutes.
Yeah, so actually the relative standard deviation is excellent here and enables a very close monitoring of the production process. That's it.
Exactly. So, and with that, I want to hand over to Hannes. He will show our instruments and give you some tips and tricks about how to operate them, sample handling, etc. And then we will see you soon for the second part, recycling. Stay in.
Yeah.
Thank you, Adrian. Thank you, Kai. Welcome, everyone, to our first lab session. My name is Hannes, and now I would like to show you the S2 Puma a bit more in detail. As you can see, it's a compact system equipped with an XY loader and touch control. The 20 position tray here holds the steer rings, which can facilitate powder samples, solids, pressed pellets, as well as liquids. The grabber will load these cups over here into the sample chamber, and operators can run the whole system via touch control with a simple press of a button. And this is actually the ideal setup for any type of process control or production control, because you have the maximum flexibility. You can have different types of samples in one run with different atmosphere modes, and the operators do not have to think about which sample needs to come first, or they have to wait until an analysis is done, because loading and unloading of samples can happen at any time, even while an analysis is running, without any interference. So this really provides high flexibility, and people have to spend minimum time on actually running the analysis. Now, as you can see here, the tray can also be removed, which is perfect if sample preparation doesn't happen near to the system. So with this, you can also prepare a whole sequence of samples and just load a completely new tray. Yeah, typical samples like this liquid here can be loaded, as well as pressed pellets. Now, especially if the system is used for multiple purposes, for instance, analyzing the liquids as well as the dried hydroxide precursors, we built in a so-called liquid cup detection, which is essentially a fail-safe for the system. So even if the operator starts the wrong analysis, the system itself will recognize a liquid cup and not run the wrong type of analysis on a liquid. So if this happens, instead of loading the sample, the system will just continue with the next sample, giving a warning so that the operator can later on correct his mistake without interfering the whole analysis sequence. So, and on top of that, we also have additional positions here in the back, which are fixed for quality control. And these can also be automated and programmed so that operators do not even have to deal too much with quality control. This can happen automatically to monitor the state of the system and the status of the calibration itself. Now, speaking a bit about calibration, typically, especially in the case of liquid precursors, this is done with calibrations which are fairly easy to set up, especially for these liquid precursors, because as you have seen, all you have to do is pour a liquid into such a cup. There's no further dilution, no complex sample preparation. It's just fill in the liquid into a cup and measure. So this is overall a very fast and easy way to deal with the samples. And overall, especially for this application, the S2 Puma can take a huge load off other techniques like ICP, where the whole sample preparation is just a bit more complex and takes more time away from people to deal with other analysis they have to do. So here, the S2 Puma is a really a game changer for people, making life easier. And that's all I wanted to show you. Back to the studio.
Yeah, thank you, Hannes, for the nice show of the demo lab and our instruments. And now comes the sad part of our story. We have used the car and actually the battery is damaged, is out of order. So what about the car battery recycling? Let's have a closer look.
Yeah, this is of course then the end or the beginning of the battery value chain. So we are also very interested in what we can do with these resources. As mentioned, there are quite some valuable resources in the batteries, especially cobalt, nickel, and copper, which can be recovered. And as you can see here from this map, there's currently also a huge demand for recycling facilities. And with a huge demand for recycling facilities comes also demand for analytical solutions to help recycling companies to basically get the material in the quality outside their processes and then re-enter it into the battery manufacturing. So there's a big also governmental part in this game, of course. So especially the European Commission has set boundaries for how much material, how many batteries have to be recycled. So and this is upscaling over the next couple of years significantly. And there's also rates for how much of the recovered rate of the recovered material has to be going into new batteries in electric vehicles in particular.
It's actually, it's not a burden. On the one hand, it's a benefit because we learned that about 16% of the value of a car is hidden in the precious metals, and they are really precious like the cobalt. Let's have a closer look how the recycling of battery works in detail.
Yeah, exactly. So here you can see a bit of an overview of the recycling processes for lithium NMC. As one example, this is one of the materials that is significantly used in the electric vehicles and where a lot of thought and brain is currently put into how to properly recycle these in an also cost-efficient way. And as you can see from this picture already, it is quite complex. So there are various ways how we get the precious metals, in this case, copper, aluminum, nickel, lithium outside the batteries and back into the production value chain. Typically, these recycling processes involve some sort of mechanical disassembling, shredding, separation process. So once you have removed, for instance, the shell of a cell and the racks, then you have to shred the inside of a shell. And this is a quite energetic process. So you need to in order to avoid combustion, for example, or hazardous moments, you need to do this on an inert atmosphere. And then you have at some point what we call the black mass of a battery, which contains a lot of the cathode material, which is quite valuable for us, but also some residual graphite material, for example.
Means actually we know what we have in a battery cell. It's the aluminum packaging, it's the polymers, it's the copper foil, the electrode. There will be remains, and then the cathode and the anode material. And of course, yeah, we need to handle those.
And the analytical parts here come mostly between that shredding step and then the hydrometallurgical step. So the one plant wants to know how well my shredding process works, and the next plant wants to know, well, how much is actually inside. So and this is where XRF comes into play. So XRF, like the S2 Puma here, is really a nice tool. Maybe Kai, you can spend a few words on that.
Yeah, it means we receive this material and we want to determine the commercial value. So especially how much cobalt, manganese is inside and nickel. And the benchtop XRF instruments are very ideal. The S2 Puma has enough excitation power to determine all the necessary elements on the other one hand. And on the other hand, it also has some precaution because we learned it's pretty nasty samples and there must be some precautions in the instrument. And when we look inside, actually we see here that there is the sample. And of course, it's a cup with a thin foil on the bottom. Of course, it may happen that the sample, the foil breaks and the powder is released. And of course, therefore, we need to, on the one hand, avoid contamination of the X-ray tube. This is a pretty expensive component, and therefore, the S2 Puma has a filter wheel in front of the X-ray tube, and there is a filter to protect the X-ray tube head. So at the point of breakage of the foil, the powder will not enter and damage the X-ray tube itself. On the detector side, we have a detector with an entrance window. It's a semiconductor detector. We can imagine it's a very complex technical equipment, and we need to protect. And the S2 Puma comes with a dust shield in front of the detector. So when we have spillage of liquids or we have loose powders there, the shield avoids the contamination, and in case something happens, it's quickly exchanged. So in the moment something has happened, there is a small reservoir, and in this reservoir, the particles are collected and can be cleaned by the user themselves. So there is no need for an additional service visit of an engineer.
Yeah, so even in really difficult environments, our systems are ready to perform 24/7. That's basically the take-home message here.
Exactly. Yeah. So then, of course, we talked about this fact. We can work with loose powders, and that's the very straightforward way. In the moment where you receive the material and we want to be a little bit more accurate, we want to have a little bit more precision, it might be useful to press the sample into a stable pellet, which is just an investment of 1 additional minute. And you can see the effect here comparing the two spectra. The lower ones is the loose powder, and this top one is the pressed pellet spectrum. And you can see there is an additional plus in intensity, actually because we are compacting the powder, we are getting rid of the air in between. This leads to a higher intensity.
However, the simplest way remains the liquid cup and loose powder analysis, right?
Means the liquid cup, it's pretty easy assembled. You see here the 4 pictures. You have 2 plastic rings. You have the foil in a paper frame. You put the foil between the 2 rings and press the top ring slowly down. And then actually you have a cover. After you have filled the cup, you can close the cup with a plastic cover. Typically, those samples can be analyzed in helium mode for very light elements like sodium, manganese, magnesium. In the moment you look for medium or heavy elements like nickel, manganese, cobalt, we can use the air mode, and the intensity is high enough. Yeah, you simply put the sample cup on a balance and fill in about 7 grams per samples. And you see here on the right-hand side the picture of the manual loading. So that's the easiest way when you have a few samples per day. This would be sufficient. When you have more samples and you want to run sample series, then actually you would select the model with an XY changer.
Yeah,
right?
and if you get to the highest throughput, that's something we haven't mentioned yet. You could also even hook up the whole thing to an automated sampling procedure. So all our systems, the benchtop systems and the wavelength dispersive large floor standing units also can be equipped with an automation interface for automatic sample receival for highest throughput.
Yeah. So I guess it's now time to look at some results, right?
Exactly. So now when we think about recycling, we need to keep in mind that, well, the material can be quite diverse. Depends, of course, on where you are in the process. Later on in the process, you might know much better what you're dealing with. Early on in the process, you might just have a black mass and you have no clue what's inside. So this is where one of our solutions comes into play, and that's called SmartQuant. So SmartQuant is a standardized solution working on full fundamental parameter mode. It's available for wavelengths and energy dispersive systems, and you can really use it to measure complete unknown samples. And we want to give you an example here for some black mass samples, completely unknown, that we've measured with SmartQuant. So SmartQuant comes with some ready solutions, for example, to measure oxide, smart matrix, but you can also fine-tune it. So you can give it some more information about your sample. So you tell it, for example, it's a powder, I added so and so much gram into the sample, and I know that in a black mass, for example, my matrix should be something carbon, so it should be probably graphite. If you enter that material, you will improve your data quality. But overall, the system really provides you the guidance of what to use. For example, to use for light elements rather low excitation voltages. It provides the best selection for the filter and also gives you a first indication about the counting times you should use.
Yeah, difficulty in those recycling applications is that we typically don't have any calibration material. Yeah. So SmartQuant is the way that you can set up the method and use the calibration behind SmartQuant in order to make your own calibration and provide the information and store in your own method. And so in daily life, this looks that you define the button with the information you have, and then the operator simply need to press the button and all information is taken from your default application. And typically data quality should be okay, right, Adrian?
Exactly. And so with the press of a button in a few minutes, like Kai said, you get the results. Here you have examples for a couple samples. You get all the concentrations of the major elements. You get the concentrations also of the minor elements, so at a percent and below percent level. And even some trace elements can be quantified quite robustly with SmartQuant.
Yeah. The good thing is typically in a calibration you have elements of interest. So you would calibrate, in this example, maybe nickel, manganese, and cobalt. Nevertheless, in a recycling process, there's always a way of contamination. There will be some foreign material which is going inside, some other metal parts which are shredded and suddenly show up in your fraction, the blast max fraction, and suddenly you see some elements which you don't expect, like titanium. The good thing using SmartQuant FP is then that the titanium will be evaluated and show up as a data point. So you would see, hey, I have a contamination in my material. And so this is especially important for people who are buying black mass for further refinement. Means it's easier for the primary supplier because he might know exactly the battery cell type, and therefore he can react and better sort the material.
Yeah, exactly. When you need more accuracy, and for example, let's say you are already recycling only lithium NMCs with a certain type, and before selling the big bags to the next company or before receiving those, you want to check, then of course you can also calibrate the system. Here's an example for that, where we calibrated the system with a range of different NMCs. You can see, get an idea about the precision again on a similar level as we've shown before. This is also the type of result quality that you could expect in the upstream process when looking into, let's say, hydroxide precursors. And again, you can then determine thresholds to make your decision life easy. And also, if you have these recycled values, you might use the same device up on shipment and up on receival. You can easily check against each other and know the value of the big bag.
Yeah. The good thing is, again, we can put in some limits and see the check marks. So we don't even need to look at specific values, but see immediately, okay, this is in spec, or we can sort for specific material grades.
Yeah. So, and with this, I want to hand over to Hannes again, who will show us a little bit more about measurements of black mass, for example, on the S2 Puma. See you later for the Q&A session.
Welcome back, everyone, to our second lab session. In the first one, we had a look at the system itself and some typical applications from the assembly and production of battery components. Now it's time to look at the end of the battery life cycle, because as we've seen in the presentations, batteries contain a lot of valuable resources with ever-increasing demand. So the recycling of the batteries become a ever-growing and more important topic. And when we talk about battery recycling, we talk about not only the big car battery packs, but also all types of consumer electronics, like this notebook battery, but also things like these we all know from our daily life. And the recycling of these batteries works that they are first collected, sorted to some degree, but at some point they are shredded as they are, which means the resulting material will contain all kinds of materials. Plastic casings like these, residual metal particles from the metal casing in this case, and it's a wild mixture of materials. The end result of the process is what we call black mass. So a blackish, heterogeneous powder with still some plastic parts and metal pieces inside. But on top of it, it also contains our precious resources and the anode material, which makes it overall quite a challenging material to do elemental analysis on with any technique. However, with XRF, we have the big advantage that the sample preparation itself is still very simple and easy for us, and really straightforward. We can simply pour the powder into a liquid cup like this and analyze it as a loose powder. And since it's still a quite heterogeneous material, you're always looking at higher sample throughput to get better statistics. And it's also possible to prepare the material as press pellets, which would open up the possibility to use automation on the S2 Puma via conveyor belt and automatic sample preparation for even higher throughput. But overall, it's quite a challenging material for the analytics. Speaking of which, what do we actually want to analyze in this case? As we've seen in the presentation, there are different aspects here. One, of course, is the content of these valuable metals, but also their ratios. And there are different sides to this. While for a company actually doing the recycling, it's more important to see not only the concentrations of the resources, but also the ratios. And they also want to look at other components, for example, these residual metal particles from the metal casings to see how well the recycling process actually works. On the other hand, companies who want to recover the metals from the black mass, they are more interested in the absolute concentration and the ratios to see what kind of material it is and how much they have to further treat the material for their processes. In any case, it's a very heterogeneous material changing on a daily basis. So it's not ideal to analyze this with a calibration because it's simply impossible to cover all the different changes that might occur in the material itself. So this overall is a very nice application for a standardless analysis by XRF, which would be SmartQuant FP on the S2 Puma. It is a fitting algorithm based on fundamental parameters, ideal to deal with such changing materials. On top of that, SmartQuant can be highly customized. So even if most of the time only the absolute concentrations or the ratios of the valuable resources are important, since it's ED, there's still the full spectrum available so that other elements can be tracked too, like copper from metal casings, for example. And now let's have a look how this would look like in practice. So the sample is already placed on the loader. So all an operator has to do for analysis is select the right method, put in a sample ID, and start the analysis. Now we can see that the grabber moves over, picks up the easy load cup with a sample. The shutter opens and the grabber moves over, loads the sample inside, and then the analysis is completed within a few minutes. And this is all I wanted to show you. Back to the studio.
Thank you very much, Hannes, for your presentation. And now we are back in the studio. I would like to provide you now with a summary about our seminar. The main XRF applications along the battery value chain are on one hand in the upstream process, and there they involve the raw material identification and the quality control, for example, of the metal salts and solutions, of the graphite which is used there. And as well for the stoichiometry analysis of the various metals or the purity control of the precursors or the lithium NMC oxides, for example. And then on the other hand, in the recycling process, XRF is used to analyze the black mass, and there it's important to determine the type purity or the value per ton. We offer quite a wide portfolio of different XRF instruments, from benchtop EDXRF systems to fluor standing WDXRF systems. And depending on the application, various instruments are recommended or typically used there. So for example, for the mining and mineral beneficiation, the WDXRF systems are used for coal, copper, and aluminum matrices, while the S2 Puma is used for nickel or cobalt mines or smaller mines, for example. The raw material identification and the quality control, there our SmartQuant packages are quite useful and often used. The S2 Puma or the S6 Jaguar is used for the NMC salt and solutions determination, while the fluor standing S8 Tiger is used for the analysis of graphites or the analysis of traces in lithium salts, for example, sodium. Typical application related to the cathode material, for example, is the S2 Puma or the S6 Jaguar, which is used there, or for the battery recycling process, the S2 Puma and S6 Jaguar as well. And with this, I'd like to thank you for your attention. And now I would like to hand over to our Q&A sessions with our experts.
Okay, yeah, thank you, Frank. And yeah, we are ready to take the first questions, and you are very active here. Let's start with an easy one, Adrian. What is or how would you determine whether you are using energy dispersive or wavelength dispersive XRF for battery applications?
So one of the factors is, of course, well, how much performance you need in terms of trace element sensitivity. But another one can be especially when you're looking into lighter elements, such as fluorine or sodium, especially to the lower concentrations. This is typically where you benefit significantly from a wavelength dispersive system. You have a better peak separation, a better signal to noise ratio. So for instance, if you want to measure residual fluorine in samples or sodium, this could be a good task for S8 Tiger or S6 Jaguar.
Yeah. One of the questions which was coming up maybe from an XRD or XRM micro CT user. So how to tackle cell chemistry when using XRF? So can you analyze XRF elements directly in a cell, or?
We cannot look inside the cell. So you can analyze basically every material that is going into a cell. So the raw materials that are going to make the cell, and let's say the precursors, like intermediate products, but we cannot look straight into a cell. There may be some few use cases, let's say, where you say you want to cut a cell and you want to look inside. So the S8 Tiger has a mapping function, so this might be one of the applications where you can have a less destructive way, but it's rather rare.
Yeah. One of the questions which are relating to this when looking to the cells and especially in so recycled materials, the question is how do we handle this matrix effects, like looking for the heavy or transition metals like manganese and nickel, and then considering there are amounts of carbon and aluminium inside after you're shredding, for example. And the interesting thing in XRF is that those inter-element effects are basically theoretical factors which are known from physical determinations. So they are in a library. This is the one thing. So matrix effects are taken into account. The nice thing in XRF is also there are some indicators, means we always look for 100% of the sample. So the missing part would be non-measurable elements, for example, and this is so-called the rest to 100. And then actually there's also a rhodium Compton signal, which is an indicator of the overall matrix of the system. So with the theoretical and fundamental parameters, and knowing the rest to 100 and the Compton ratio, we can always almost get very accurately to 100%, and also correct for effects like changing carbon values or changing aluminium values. Yeah. The question here is kind of interesting. How would you address fluorine measurement in black mass when we are doing recycling?
Yeah. So fluorine has a very shallow penetration depth with X-rays. So we get only information from the very, very near surface of the material. However, we can still measure it relatively precisely, even to lower concentrations with especially wavelength dispersive systems. But that would mean that you have to press the sample. So you cannot use it in a liquid cup with a powder or a slurry. You would have to press. There are multiple ways to do this. If it is a material that is a bit wet or slurryish, it might be a way to put it on a substrate and dry it. Or if it's dry anyway, then you can typically press it. Maybe you have to add some binding to get a good solid pellet out of it. But then you can measure residual fluorine concentrations also to, let's say, the higher hundreds of ppm or 1,000 ppm, depending on a bit on the substrate.
Yeah. There's one question which is kind of interesting because this might come from an ICP user. The calibration curves for liquids we have shown are close to a correlation coefficient of 1. And but what about the range over which you get this level of linearity? Yeah.
Yeah, so the linearity is relatively wide, but there's also factors at which the linearity goes a bit off, and this is when you have what Kai said, the matrix effect. But our software is essentially capable of compensating that. So when the matrix changes, basically, easy way would let's say you have a copper ore and that in mining that you enriched step by step to something that is a concentrate which has high concentration of copper, for example, then you can have this all in one calibration, and the software essentially accounts for the changes in matrix. However, there might be circumstances where you could also have the situation to subdivide into different fractions. So where you focus just on the traces in one calibration and just on the high elements.
Yeah. This is also the question related here. I will take this. Means how does the software know if you analyze traces or majors? The good thing actually in XRF is that you have a huge linear range. You don't need to dilute samples. So the software or the instrument can handle ppm to 100% in one go. The interesting thing, we have stored in a line library the optimal conditions to analyze traces, avoiding line overlays. So whenever you are starting and preparing a method, actually the software will propose those measurement parameters. And also in terms to reach a better accuracy or higher precision, also the software can have multiple measurements for a single element in wavelength dispersive. So it would mean there's a setting for majors, and it would mean there's a setting for traces, and then it uses the setting which are related to that count rate. Yeah. So there, XRF is pretty robust compared to liquid chemistry and doesn't need a digestion, as I said in my presentation. So actually, that's a big advantage when we are dealing with 100%, 50%, or traces. There is another question. Please explain the benefits of XRF over LIBS. Means when we look at recycling, often LIBS comes in discussion. And of course, laser-induced breakdown spectroscopy is looking at surfaces. The major difference between those two methods are we are a bulk analysis method, XRF, so we are looking at larger material amounts, a larger material volume. LIBS actually look at a small spot where the laser hits the surface and actually creates the plasma. And this is the major drawback. It is a good micro technology, but when you look at ground material, powdered material, you will get random numbers. If you hit a carbon spot and then you hit a cathode spot, and you need to hit an aluminum spot, so it is not very accurate, despite the fact that they are promised to do very good analysis on the fly. Nevertheless, material is inhomogeneous, and we are showing a pretty good mean value there.
I mean, a common use case there would be rather when you look into metals, alloys, which are then really homogeneous, where when you hit a spot here, you hit a spot there, that should be the same composition. But in the materials we're dealing with, battery, you don't have that advantage from the sample type.
How would you compare XRF and ICP in terms of impurities?
Probably in terms of impurities of detection limits, or Okay. So they're essentially for many of the elements of interest that we are caring about in battery manufacturing and battery recycling, you can obtain similar or equal detection limits and precision with an XRF system. Of course, and when you go to the, let's say, real low concentrations, especially of, let's say, light elements, like a few ppm of sodium or low concentrations of fluorine, that's when you reach the limits at some point, or let's say some traces that are really sub ppm or ppb level. This is then something that you have to do with ICP at some point. But for the majority of the applications that we see in elemental analysis related, especially along the production process and in the recycling process, XRF has really a number of advantages.
Yeah. There's one question regarding the analysis of lithium, especially in battery applications. Will XRF ever be able to detect lithium? And yeah, so actually both wavelength dispersive and energy dispersive technology are not the suitable technology there. The one thing one needs to know is that the sensitivity, the X-ray radiation is very weak, so it will be easily absorbed by any material which is in the way, like the detector foil or the air between the sample and the detector itself. So this is the one thing. The second thing, which is more critical, there is not much fluorescence radiation coming. Most of the energy is expelled as an Auger electron, and this cannot be detected by our instruments. There must be ultra-high vacuum devices. So there will not be a way to determine lithium directly. What is good, as I said, we can access the matrix indirectly, and this already is a very big help to get a kind of estimation about the range, and often this is good enough. Means we have instrument installed in lithium mining application and doing the same thing, that we are analyzing the rest of the elements, and then knowing the stoichiometry, we can pretty good estimate the lithium content. Yeah. So let me quickly check that we have covered every question. The quantity of the sample amount required, could you make a statement there, Adrian?
Yeah. So as you've seen maybe a little bit in the part Hannes has shown you, like a typical material amount is on the gram range, so a few gram, 5 to 10 gram of sample or milliliter that you put in a liquid cup, or if you press a pellet, we typically use like 8 to 10, 15 gram of material. However, if you're in a situation where you have less sample, there are also ways to deal with it. So you can, for example, either smear it if it's a slurry on a substrate, or like a little bit of a cup, or you press it on some substrate. That's possible. And also for larger amounts or larger samples, there are some ways to deal with it in XRF. But that's a rough estimation of them.
Yeah, one of the, or maybe the last question we are answering today, concerning measurement accuracy, which deviations can have or which deviations can be seen concerning the grain size particle effect?
So the grain size has an effect. Let's put it this way. Normally, a bit of a sweet spot for XRF, where you get the let's say the best signal and also from your data is like on the order of a few tenths of microns, so 40, 50, 60 microns. That's ideal. But you can also get very robust results for much larger particles. So the point is a bit is how reproducible is your grain size. So if it's really a wide spread, so sometimes it can be more coarse, sometimes it can be finer, then we would recommend to sort of put it to a common ground, so like basically grind it. The material we've come across so far may be black mass recycled or like a precursor material that is typically suitable as is. So there we haven't come across much challenges with the grain size.
Yeah, so when we have a very good material, we are at a range of 0.05% relative best. Might be slightly less correct for major elements in the moment the material is more coarser. And with this final statement, I would like to thank you for your time, and it was really nice to have you with us here in the event. And yeah, I'm looking forward to see you next time. We will answer afterwards the open questions, and you will receive the recording and the material later on.
Yeah, thank you very much also from my side. Have a great day and see you hopefully next